The other conic section I'm going to talk about is the parabola. Now, we're familiar with parabolas because we have quadratic functions that graph to be parabolas. We never really give you much of a definition of what a parabola is. And so this is kind of based on that. We're used to seeing parabolas as functions and graphing quadratic functions, but not all parabolas are functions. So you're going to see some different parabolas. A parabola could go, right side up like we're used to seeing, something like that, or it could go upside down, or it could go to the right, or it could go to the left. Oops, I didn't go to the left. So I'm going to do these a little more in detail, the different cases, on another screen, so we'll have a little bit more room. But let's just take a parabola. We'll just take a parabola that maybe you're kind of used to seeing. That's not a very good parabolic shape, but something like that. We know there's a vertex for the parabola. And we know that the axis of symmetry goes through the vertex. Okay, so that would be the axis of symmetry. All right. And we know if we fold the paper along the axis of symmetry, the points on the left should line up with the points on the right. Okay, now we have to talk about some of the parts that we haven't maybe talked about a lot before in the past. So there's a focus for a parabola. So it's somewhere in there, okay? And then there's this distance between the focus and the vertex, and that distance is P, okay? All right. When you go to the other side, so if you go P distance to the other side, so another P units here, and you put a point there, and you draw this line, in this case it would be a horizontal line, that is called the directrix. So the directrix, the vertex is halfway between the directrix and the focus, if you were to draw like perpendicular lines there. Okay. The definition for a parabola is if you take the distance from any point on the parabola and take that distance to to the focus, that's going to equal the same. So let me draw this out because it's hard to explain. And my parabola is not drawn very well, so probably won't work visually, but there's a distance here. I want to do that in a different color. There's a distance here, some point on the parabola. And then if you drop from that point, if you drop a perpendicular to the directrix, those two distances have to be equal. Now, obviously, my parabola is not right because those distances aren't equal, but pretend like I drew a good parabola, and that would happen. And you could do that for future parabolas. You can see that, okay? All right, now we've talked about everything except the latus rectum. So, let's see, I need another color. All right, if you take where your focus is, so this is the focus, remember that. And we only have one for a parabola, just one focus. And draw a line parallel to the directrix. So, you're going through the focus and then you're going to the parabola. That's a line segment, and you get endpoints right here. The line is the latus rectum. And then the endpoints of the lattice, we call those the endpoints. So that's one endpoint of latus rectum. And then the other endpoint's over here, okay? So you have this line segment with two endpoints, and those are points on the parabola. And that's why it's helpful to find the endpoints of the latus rectum, because then it gives you two more points that are on the parabola. So we're used to doing kind of different parabolas with quadratic functions. We get nice little shapes, that fit on the graph paper and stuff. These parabolas, sometimes they're very wide. You can get a skinnier one, but it just has to do with where that focus and directrix are. Okay, so let's go ahead and do an example here. Oh, I said I'd talk more about those different ways the parabola can go. So let me get a new page. Let's see. What I need is right under there. Okay, so let's say we have a parabola like this. Oh, let's not have that. Okay, let's say we have a parabola like this. It's opening up, right? The focus would be right here somewhere, and the directrix is going to be underneath. The directrix is never going to go through the parabola, okay? So sometimes I see that mistake on tests sometimes. You have that distance P, so this distance is P, and this distance is P, okay? So you have a parabola. From the vertex, you go P units to the focus, and in the other direction, P units to the directrix, okay? Now, if you have a parabola going this way, then your focus is going to be in here somewhere, and your directrix is going to be above in this case, okay? So we usually draw that dotted line for the directrix. Okay, now, those cases both have x squared equal 4p. I'm sorry, 4py. Okay, so that's the formula for the parabola. And these, by the way, all of these are going to have a vertex at the origin. So let me write that someplace. Vertex. And again, you could move the vertex to a different location, but I'm not going to worry about that right now. All right. And then this one is also x squared equals 4py. Here, p is greater than 0, and here, p is less than 0. Okay? All right. And we're still keeping the vertex at the origin. So now let's do some sideways ones. So say you have a parabola going sideways like this, opening up to the right, I guess. So your focus is somewhere in here. Your directrix is back here, okay? And the equation for this is going to be y squared equals 4px. And in this case, p would be greater than 0. So we have a lot of information here I'm giving you, and I, hadn't planned to write that all out right there, but that's how it is, and you'll need that. So the other case is if the parabola opens to the left. And again, your focus is going to be inside here somewhere. Your directrix will be back here, and the equation is going to be y squared equals 4px, but p is less than 0. Okay, so now we'll show you an example. Okay, so it says graph y squared equals 24x. Identify and label the focus, directrix, and endpoints of the lattice rectum. Okay, so they asked for those endpoints of the lattice rectum so that we're getting some shape to our parabola and we're not just drawing it, poorly like I have on these examples. Okay, so here's our equation. And by looking at that, we know a couple things. We know that it's going to be a sideways parabola, so it's either opening to the right or the left. Now you want to look at that 24. That 24 has to equal 4p, okay? That's important because we want to find p. So we're going to divide both sides by 4. I don't know why I'm writing that out. 6 equals p. Okay, now this is going to have the vertex at the origin. So my vertex, I should emphasize this more. All of these examples I've been doing for the parabola have the vertex at the origin. You can have the vertex somewhere else. I'm just not going to go into that for these, for this section. We only have so much time. Okay. So my vertex is here. I do want to draw my vertex. So there it is. My p is positive, right? So since p is greater than 0, it's going to be opening this way, okay? So I'm going to count my units, 1, 2, 3, 4, 5, 6, and I'm going to graph the focus. So right there, that's the focus. They asked me to graph it and label it. So that's the focus. The focus is not on the parabola. Okay, now I'm also going to do the directrix, which is going to be in the other direction. So 1, 2, 3, 4, 5, 6. And it'll be this vertical line back there. That will be the directrix. Okay, now that's a lot of information. I know how my parabola is going to face, but I don't have the actual shape. And so what I want to do is I want to find some endpoints of the lattice rectum. What you're going to do then is you're going to let x, let x equal p. Okay, and so I'm going to plug in a 6 for that. So I'm going to get my equation here. Y squared equals 24x. And so y squared equals 24 times 6. And then that's going to give me y squared equals, what's 24 times 6? 144, sure, no. It's a nice big number there. And so I'm getting y equals plus or minus 12. Well, what that means then is I have two endpoints for the lattice rectum. So let me draw that. Well, it's going to be a little big, but that's okay. The lattice rectum then is going to have endpoints. Let me write. Endpoints are going to be 6, negative 12. That's one of them. And the other one's going to be 6, positive 12. So what we're doing is we're plugging in the value 6 for x. And I always remember how I know which one it goes into for x or for y. You can look at the graph, but it's always the one that's not being squared. So, because when we take the square root, that's going to give us the two endpoints. Okay, so now what I want to do is I want to count up 12, which doesn't really fit, and down 12. Sometimes these are real, oops, I'm off a little bit there. Where's that? So up 12 and down 12, negative 12. And so I get this huge parabola that's going to go through the vertex, which is at the origin for our problems that we're doing, and then it goes through those two endpoints of the lattice rectum. So I didn't identify those, but so you could draw that in, I guess. If you wanted to draw the lattice rectum, it's right here. Sometimes they'll do that, but these are the endpoints then. 6, 12, and negative, or 6, negative 12. Okay, those are those two endpoints. All right, that's it.